I'll send them an email.
Okay.
Okay. Should we start?
Yeah, sure. Yeah.
Okay. All right. So, well, hello everyone. Welcome to this CAV 3A session on AI verification. So just a reminder, right after the session, there is a social breakout session, and you can find the Zoom link on the online program. So please join right after the session. And during the talk, you can use Slack to post your questions. There is for each paper, there is a channel, a thread on the main track papers channel. So you can please go there and to post your questions, and I will monitor it. And right after the talk, there'll be a Q&A session. So the very first talk of the session is given by Stanley Bach from Stony Brook University, and he will present various improvements to the StarSet method for analyzing neural nets.
Hello, I'm Stanley Bach, and this is the talk for improved geometric path enumeration for verifying ReLU networks. I'm going to be joining as an assistant professor in the fall in Stony Brook University, and this is also collaborative work with Hongdong Tran, who's a graduating student at Vanderbilt, and Taylor Johnson's group, who's also in Vanderbilt, and he's going to be also joining the University of Nebraska in the fall as an assistant professor. And Carrie Ann Hobbs is also on this work, and she's with the Air Force Research Laboratory. This paper is about neural network verification. So specifically, it's about the open loop neural network verification problem, where given some constraints on the input set, we want to prove properties about the output set. And so in particular, it's about evaluating improvements to the StarSet analysis method. So StarSets are a data structure that encodes a set of states that sort of works really well for analyzing certain types of neural networks, in particular neural networks that are fully connected with ReLU activation functions. It also, there's extensions to convolutional neural networks and max pooling layers and things like that. But for this talk, I'll be focusing on ReLUs and fully connected layers. So the reason they work well for this class of systems is that using star sets, you can exactly encode linear transformations and intersections in high dimensions. And so this means you can do exact analysis actually for this class of networks. So for example, given ranges on the inputs, I can tell you whether I can compute all the possible outputs in terms of sets, and then you can say, is a particular output possible by just doing set operations. So this is different than testing. It's sort of like exhaustive analysis. So ReLU activation functions compute the maximum of the input and zero. So if you look at the input-output space, it looks something like this, where the inputs are on the x-axis and the outputs are on the y-axis, right? So analysis is challenging primarily because these systems have both the chance to have negative inputs and the chance to have positive inputs. So it's really like a piecewise linear function. If it was an exact linear function, then you can analyze in very high dimensions. So it's not always difficult though. So for certain neurons in your network, if you could prove, for example, that the input is strictly positive, then you could show that the output is just identical to the input. So it's an identity transformation. So it's a linear transformation. And sort of likewise, if you can prove that the input is strictly negative, then this also means that it's a linear transformation because it's just a projection to zero. So really the difficult case is when you have neurons in your network that have inputs that can be either positive or negative. And so as I was mentioning before, with star sets, the nice thing you can do is if you're interested in exact analysis, you can split the set into two using an intersection operation, and then sort of proceed recursively through the rest of the network. So the analysis sort of proceeds neuron by neuron through the whole network. So you could imagine if your layers are numbered from 1 to 5, and then at each layer you have 100 neurons, you could start with layer 0, neuron 0, and check if the inputs can be negative or positive. And then depending on which situation you're in, you can either proceed with just a linear transformation or split it into two sets. So in the worst case, you're going to be splitting exponentially, but in the sort of common cases, maybe you can get away with doing this and completing analysis. And so there's other options too, which I'm not going to really look at in this paper. So in particular, there's this triangle over approximation. So if you look at the original star set reachability analysis paper in FM 2019, they also talk about, instead of splitting, you can do over approximation. So here it's this is like the optimal convex relaxation of the ReLU in this 2D projection space onto a particular neuron. And so with StarSense, you can actually encode this as well, and do it efficiently too. And so the last sort of way to encode these ReLUs is what are called zonotope over approximations. And so compared with the triangle over approximation, there's actually more error. If you look at the let's just say the area in this projection, the possible outputs for possible inputs, depending on the possible inputs, the zonotope is going to have more error. But the advantage is it's faster to compute. So with the star set, if you want to maximize a function over a star set, it's a linear programming problem. With a zonotope, maximization or minimization can be done in a simple loop, so it's significantly faster, but the cost is sort of you have more error. So I mentioned we want to do neural network verification, and exact analysis is possible. And so the way this works is that you analyze the inputs for each neuron and then compute the possible outputs. But as you might suspect, based on the strategy where you might split at each neuron, verification can actually take exponential time. So there's proofs that it's sort of NP complete. So if you have a network with 300 neurons, which is not a huge neural network, now you in the worst case could have 2 to 300 sets. So it's obviously not manageable, right? You can't enumerate 2 to 300 sets using a sort of exact strategy. And then so the question becomes, okay, this is the worst case. Does it happen in practice, right? So just because this problem is NP complete doesn't mean we don't try to solve it. Like SAT solving is NP complete, or software verification maybe is undecidable in general, but we still have effective techniques to work on these problems. So in order to say whether this method is feasible in practice, you need to define what you mean by practice. What are the benchmarks that we run on? And so in this paper, we focus exclusively on the ACAS-XU system. So the ACAS-XU paper from 2017 is kind of a popular paper now. I think there's about 500 citations in just a couple years. And what's neat about it is, they have analysis methods proposed that they use, but also they have a nice set of benchmarks. So it's a system that's supposed to prevent collisions among two aircraft, so by issuing turning advisories. And so the reason they're using a neural network rather than something else is that they had this sort of large lookup table of rules that you should follow, and they found out actually using neural networks you get a nice compression of this. And so the motivation is, well, in avionics hardware you can't have you can't have too much memory, so this compression might make a difference, right? But then the question is, okay, you've done the compression and it's not exact, does it still maintain safety of the system? So this is what the ACAS-XU system looks like sort of in simulation. So this is sort of closed loop simulations now of the system. And so you can see there's two aircraft, and so the one on the top is the intruder aircraft, and the one on the bottom are the own ship aircraft that's running the ACAS-XU system. And depending on the initial state that you start in, you might get different sort of turn advisories, right? So this is a closed loop version. The open loop version just looks at, let's say a single point in here. What is the advisory that's issued? And then proving properties about the advisory. So for example, in this sort of head-on collision scenario, one advisory you might want to be able to prove that some advisory is issued. It doesn't give you the clear of conflict command. If there's this head-on situation, you should either turn left or turn right. And so that's actually, that sort of property is what's defined in this ACAS-XU paper. So more specifically, there's 5 inputs to the system, depending on the positions of the aircraft, the angles, and the relative velocities. There's a 300 neural network, fully connected layers with ReLU activation functions, and then it outputs 5 commands, and then the one with, I think, the minimum output is the one that's chosen as the actual output of the system. And then properties are things like what I mentioned, right? If there's this head-on situation, which you can define in terms of linear constraints on the inputs, then there should, the clear of conflict should always be the smallest. Basically, clear of conflict should never be the command that's issued, so it shouldn't be the smallest. So if you ever find a situation where the clear of conflict output is the smallest, that's a safety violation. And this is property 3 in the paper. So this paper is not about partial over approximation. This is sort of an additional thing you could think of where, instead of splitting or doing over approximation, why not do splitting on some neurons and over approximation on other neurons? That's definitely a good way to do it. But this talk is really about exact analysis. If you're interested in this method, there's another talk in VNN. that you can look out for, which is one of the workshops associated with CAV. It's also not about perception neural networks that are sort of huge in size, where you may have millions of neurons, right? So there's another talk at CAV dealing with this problem too, so I encourage you to see that one. It's really just focusing on ACAS-XU and specifically what optimizations are possible for the star set technique. And so you can't really tell you whether, I can't tell you whether it works or not unless I optimize the system. So what we've gone through is we've proposed a series of optimizations where we steadily have increased the performance from 10 to 100 times what the original star set approach was capable of doing. So let's look at the paper briefly. So if you open up the paper, it looks something like this. We've gone through the repeatability evaluation. There's a nice description of the algorithm that if you're interested in re-implementing, you can do that as well. There's descriptions of these data structures, sort of formally what I meant when I said a zonotope or what is a star set. And then there's evaluations where we look at different optimizations and we evaluate all, in this case, it's 180 different benchmarks on ACAS-XU properties 1 through 4 that are run on 45 different networks. So there's 180 benchmarks total. And then for different levels of timeouts, you can see how many properties you could verify. And so in the original work, the proposed method was similar to a breadth first search. There was a layer by layer analysis, and so we compared that with a depth first search strategy, right? And apparently, as is sort of well known in model checking, when you do depth first search, first of all, it's less memory intensive, so we can analyze several benchmarks that ran out of memory before, and it's also better at finding counterexamples faster. So we get a speed up now, and we can analyze, in this case now, in the 10-minute timeout, we can analyze over 120 benchmarks. So that's sort of like the first optimization. There's also this notion of how do you actually compute the minimum and maximum input at each neuron. And so there's several ways you can do this. So the first one is you could directly try to split the set and check for feasibility of the LP. And if it's infeasible, that means it's not, you can't split on that neuron. That's the copy pre-filter type here. There's bounds, which is just compute bounds using LP solving. There's sim, which is interesting because if you compute bounds with LP solving, you have to solve two LPs, a minimum and maximum. But actually, if you run a concrete simulation, you'll have a specific value that's either positive or negative. And if you have, if you know there's a real value that's positive, you could first try to solve the minimization LP. And if that's positive, then there's no split. So you can reject that, the branching with just a single LP solving. Zono bounds and zonosim are similar to bounds and sim, except they first do zonotope over approximation. And if the zonotope has if using the over approximation, the input is strictly positive or strictly negative, you can reject the branch with zero LP solving. So these are other ways you can speed up the analysis. And the next one is eager bounds computation. And so this is when you're going through layer by layer and a split is detected, you have a choice now. You could immediately split and proceed recursively, or you could keep computing for the rest of the layer. And so what this one does is the eager one will keep computing LPs for the rest of the layer to get the bounds on all the other neurons before doing the split. And so that's useful because if you can reject branches for the larger set, like if using a larger set, you can tell that the last neuron in the layer doesn't split. Then after you split, you're going to get strictly smaller sets, and so then those ones no longer need to split either, and you don't need to solve an LP in each of those stars. So it's really choosing where to do the work. And so you see, using eager now, we have a few more benchmarks we can analyze, and then there's also this domain contraction optimization that's described here. And so the idea here is, with a zonotope, we can't do intersections exactly, but instead we can shrink the domain of the zonotope. So a zonotope is a linear transformation of a unit box in high dimensions. So you can't split it arbitrarily. If I have this linear constraint that cuts this box in half, I can't exactly represent that with the zonotope, but I can reduce sort of the box here by reducing the Ymax, and here I have sort of a smaller box, which is, it's actually a rectangle now, but it's okay because zonotopes are affine transformations of the unit box, so this is representable now, but now it's a smaller domain. So this increases the accuracy now of the zonotope over approximation. So ways to be able to, if I can make the zonotope more accurate, I can reduce the number of LPs I need to solve. And so there's different strategies we propose for doing that. In the paper, we also evaluate against other tools. So in particular, here's Marabo, which is the newer version of Railplex, NNV, which I think there's an improved version now as well. So this is the version as of January when we did our evaluation. There's R method, and then there's the Neurify tool. And so if you look at all of the properties, it looks like Neurify actually is better for most of them until you get to the end. So our tool is actually the first one we're able to analyze, I think, all of the properties before timeout. Neurify actually times out for some of them. But actually, most of this benefit is just from property one. So property one is sort of far from the unsafe set, and because we're doing exact analysis, we can't take advantage of that. We're not using the property, whereas Neurify is. And so if you actually remove property one, that's what this plot here is on the right. And you see that if analysis takes more than 2 seconds, our method is likely faster. So that's sort of kind of neat. We think this is a good result. And there's also a table of other sort of comparisons versus tools like ERAN. So ERAN, there was some script set up to work on property 9, and so we're able to outperform ERAN on that particular property too. And so the last thing I'll say about the paper is at the very end, there's a big table of every benchmark and how long it takes for every optimization level, as well as every tool. And so this is useful if you're developing a tool and you want to have some benchmarks. You can pick what's an easy benchmark. Like let's look, say, property 3 network 2.8. This one should be analyzed in 1 second or 0.1 seconds. So that's an easy benchmark. Or maybe you want something harder. You could look at network 3 property, or network 1.1 property 3. This one takes a longer amount of time to run. So this is very useful for tool developers working in the space as well too. So that's sort of a resource I could point you to. I think the last thing I'll say is that because it's exact analysis, we can actually visualize the reachable set over each layer. And so that's what this is showing here. This is ACAS XU neural network 5.1 property 3. And so what we're comparing is we did some random samples of the initial set, and then we're projecting things onto 2 dimensions. And so basically, if you look at the difference between the random simulations and the exact output set, you start to see some discrepancies, right? So like here, there's a large portion of the state space, or a large portion of the reachable set that's possible, but you don't get there using random simulations. But using our approach, you can actually, pick a particular target output and then generate inputs that get you there. So that's it. So our analysis, the sort of conclusion is star sets, you can do it 10 to 100 times faster on a lot of benchmarks. So it's sort of the jury's not out yet on which technique is fastest for these systems, and so there's competitions going on as well too. So in particular, VNN has one this year too. So I encourage you to come to that. So thank you for listening, and I'll be happy at the talk to answer any questions.
Okay, so Stanley, can you turn on your mic and camera as well? Okay, great. Hi. So there is already a question on the Slack channel. So the question is if there is a trade-off when using depth first instead of breadth first for the local search. It says you show that you win in efficiency, but is depth first less desirable in any way than breadth first?
So breadth, there's sometimes combinations, I would say, that are better to look at. So it's not just a simple depth first and breadth first search. There was a section in the appendix when we described parallelization, because when you want to explore paths in parallel, you end up actually doing the search in multiple threads at the same time, and then it's not really a pure depth first or breadth first search. I would say breadth first search is sometimes better if you can do the search in parallel, where you want to explore several sort of deep states at once. And so I think there's one property in ACAS XU where you can find counterexamples very quickly if you can do sort of this. First, you do like a breadth first search where all the sort of cores get one of the high level branches of the tree, and then they all do depth first search in parallel. So that sort of hybrid strategy, I would say, is good. But in terms of if you're just doing single thread analysis, I can't think of really a good way, a situation where breadth first is better.
Okay. So I also have a question. So your work is really seeing how far you can get by being fully precise. So I was wondering if these optimizations that you looked into can be combined maybe with some approximations also, if that might be interesting or.
So it's very interesting, and I think it's a good direction. And actually,
okay.
the NNM tool, which implements this method in the exact analysis, also includes partial over approximation analysis. And so that's what we used in VNN comp, which is again happening in a couple hours. And so we have very encouraging results on that. It's definitely a better way to analyze it. Yeah. And there's, yeah.
Okay. Okay, so there are no more questions, I think. Well, thanks a lot for the talk. I guess maybe we wait a minute just to be right on time, and then we'll start with the next video, I guess. So the next talk is by Ishaq El-Bouher. He's from Hebrew University of Jerusalem, and he will present a Seeger-based approach for verifying properties of neural networks.
Hi, my name is Ishaq El-Bouher, and I'm a PhD student in the Hebrew University of Jerusalem. Today I will talk a joint work of me, Justin Gottlich, and my supervisor, Guy Katz, about an abstraction-based framework for neural network verification. I will talk about deep neural networks, their vulnerability, verification of deep neural networks, and its complexity. I will elaborate about over-approximation in order to improve performance of verification, and how preprocessing can enable this over-approximation. Then I will present abstraction refinement mechanism for deep neural networks verification. Finally, I will show how, according to our experiments, how we improve the performance. Let's start. Deep neural networks are a machine learning tool that achieves state-of-the-art results with respect to many objectives in many domains, like computer vision, speech recognition, and natural language processing. Despite this fact, deep neural networks are vulnerable to small perturbations in the input, and hence are dangerous to be combined as an ingredient in critical systems like self-driving cars. In order to guarantee safety and overcome this problem, verification tools are applied. Given a property P and the network N, a verification tool checks if P holds in N or not. The return value is yes or not with a counterexample. One of the major obstacles in verification of deep neural networks is that this is a complete NP-complete problem. The time complexity of a verification tool is exponential in the number of nodes in the network. In order to improve performance, our approach is to use an over-approximation. So, given a property P and the network N, if N is complex and the query can take a long time, we generate network N prime, which is much smaller, such that if P holds in N prime, it also holds in N, in the original network. For example, if N is complex and P is the property that for every input, the output is smaller than 2, we can generate smaller networks, which is an over-approximation of the original network. And here the property is that also the output is smaller than 2. We can, in our approach, we generate a smaller network such that if the result if the property holds in the over-approximation, it also holds in the original network. Why? Because we require that for every input, the output of the over-approximation will be greater than the output of the original network. Then we get that if P holds in N prime, it also holds in N. Why? Because it holds in N prime. If it holds in N prime, it means that Y prime is smaller than 2, but Y prime is greater than Y. So Y is smaller than Y prime, that is smaller than 2. Therefore, P holds in N. So for over-approximation, we have two requirements. The first is the output will be greater, and the second is that the network will be smaller. Okay, so the first attempt of over-approximation is by unification of nodes. We take the two yellow nodes here, and we unify them into one node. The input edge weight will be the maximal input edges weights, and the output edge weight will be the sum of the output edges weights. And of course, we get a smaller network because we unify the two nodes into one. And also, we get that our output is greater because this inequality holds. You can see that the blue part, the left blue part and the right blue part are equal. And also that the left green part is smaller than the right green part because ReLU is monotone function and non-negative function. Monotone increasing function and non-negative function. So in this case, this works great, but this is not always the case. And in other cases, like where we have negative output edges, the same operation can lead to decreasing the output. For example, if the input is 1, the original output will be 5, and the over approximation output will be 2, which is less than 5. So we decrease the output. And to prevent this problem of decreasing the output, we apply some pre-processing phase. The pre-process split networks, the network nodes into 4 types. After that, each couple of nodes of the same type can be unified in a manner that maintains the increasing of the output. The pre-processing includes two stages. In the first stage, we split to positive and negative nodes. So, for example, we have some node V that include has both positive output edges and negative output edges. And we split it into 2 nodes, V plus and V minus, with the same input edges, like V. But V plus include only the V positive include only the positive output edges, and V negative include also only the negative output edges. Notice that the output, that for every input, the output of this network is exactly is equal to the output of the original network. So this is the first stage of the pre-processing. In the second stage, which is a bit more complicated, we split the nodes into two types of nodes: the increasing nodes and the decreasing node. And an increasing node is a node that when we increase its value, we also increase the output value. And decreasing node is a node that when we increase its value, we decrease the output value. So of course, all the output nodes are an increasing node. It's trivial from definition. When we increase its value, we also increase the output value, of course. But then we go from the last hidden layer backwards and split layer nodes. So here we have no split. We have no need to split. We have a V plus, which is an increasing node. It has positive edge that goes to the output, to an increasing node. And because if we increase this value, we also increase the output value, this is an increasing node. V minus is a decreasing node because it has negative edge that goes to an increasing node. Therefore, when we increase its value, we will decrease the output value. Therefore, this is a decreasing node. In the second iteration, we go to the previous layer, and we want to split U plus into 2 nodes, U plus increase and U plus decrease. U plus increase is an increasing node because it has positive edge that goes to an increasing node. Therefore, if we're increasing its value, we also increase this value that in turn increase the output value. So this is an increasing node. U plus decreasing node is a decreasing node because it has positive edge that go to a decreasing node. So if we increase its value, we also increase, if we increase U plus D value, we also increase V minus D value, which in turn decrease the output value. Therefore, this is a decreasing node. And also here, after this stage, the original network and the pre-processed network are the same network. For every input, the output will be equal. So after the pre-process after the pre-process phase, we have 4 types of nodes. We have 4 types of nodes: the positive increasing, positive decreasing, negative increasing, and negative decreasing nodes. Here we can do an abstraction. The abstraction step is actually the operation of unification of 2 nodes into 1. We unify 2 nodes into one node, and the output edge weight are always the sum of the output edge weights. and according to the type of the node, positive increasing, decreasing, negative increasing, and decreasing, we choose max or min, the maximal or minimal value of the input edges. For the case of a positive increasing node, you can see here that we prove, this is the proof for the positive increasing node, that y prime is bigger than y. The proof for the other cases is very similar. So when we apply this abstraction step many times, we get a network we get an over approximation of the original network. There are two methods of doing this over approximation. The first is abstraction to saturation, where we do abstraction step as much as we can. And the second is indicator-guided abstraction, where we apply sequences of abstraction steps. And after each sequence, we check if, according to some heuristics, we want to continue or not. You can see that according to our experiments, abstraction to saturation is a better approach than indicator-guided abstraction. Okay, so we generate an over-approximation in such that if P, the property, holds in the over-approximation network N prime, it also holds in the original network N. Great, but what if P does not hold in N prime? In this case, we can use the counterexample that the verification tool returns and check if this is also a counterexample in the original network. If it is, we can return no in this counterexample. But otherwise, this is a spurious example. It is a counterexample in the over-approximation, but not a counterexample in the original network. And in this case, our over-approximation is not sufficient in order to prove or disprove the property with respect to the original network. In order to overcome this problem, we use a known mechanism for formal verification of software systems. In our case, our system is a network. This mechanism is called abstraction refinement mechanism, and it does the follows. It tries to check if property holds in a network. It generates an over-approximation, an abstract network, and it checks the property with respect to this abstract network. If it holds, it also holds in the original network, as we saw. If there is a violation, the counterexample that returned by the verification tool is used as a counterexample, is examined as a counterexample in the original network. If it's also a counterexample in the original network, there is a violation and we can return false and this counterexample. But if this is not a counterexample in the original network, this is a spurious example, and our over-approximation is not sufficient in order to prove or disprove. In this case, we do a refinement. We refine the network and get an over-approximation which is more tight. Then we can continue in this loop until we get some answer. So in order to implement this mechanism, we have to implement the refinement operation. The refinement is over-approximation tightening, and is done by splitting back neurons that were unified during the abstraction. So this is the inverse of abstraction, and we get one node that include two or more original nodes, and we have to split it into two nodes. This is the refinement step. We developed two methods for choosing the best nodes to split back. The first method is the weight-based method, where we choose the node to split back by some heuristic on the difference between the weights of the output edges in the original and the current network. And the second method is the counterexample method, where we use also the information from the counterexample that were returned by the verification tool. You can see that the counterexample guided is a better approach, mainly according to the number of timeouts in the weight-based method. So experiments. In our experiments, we used Marabu as the verification tool. Marabu is an implementation of ReLUplex, which is a state-of-the-art verification tool. And we use ACASXU networks and properties. ACASXU is a drone collision avoidance systems that is under development by the FAA. And the properties were properties that were defined by domain-specific experts. You can see that using our abstraction refinement mechanism improves the results. And if we look at the numbers, we can see that the number of finished experiments is greater, and that the median runtime is smaller. In the second series of experiments, we examined adversarial properties. Unlike CAV properties, which were defined by experts, adversarial robustness is a universal property that is desirable by every DNN and hence receives much attention. So we generate adversarial properties, which checks that the output of the network does not change as when when the input slightly changes. And you can see that we use the ACASXU networks and generate our own adversarial properties. And you can see that the number of finished experiments is slightly better for the vanilla Marabu, but still the median running time is much better in our when using our mechanism. You can see that there is a 99% time reduction, and actually this emphasizes that our technique generally leads to significant improvements. Okay, so that's all. Thank you for listening and watching, and if there is any questions, we are here. Thank you.
Okay, thank you for the talk. So on Slack, there are some questions. So the first is from Pranav. Could you shed some light on how stage 2 of the pre-processing would work for classification networks which contain many output neurons?
It works the same. The output layer is still a layer that for every one of its neurons, we define it as an increasing neuron, and the left and all the process is the pre-process is the same.
Okay. Then the next question is, it would be interesting to consider similar ideas for under-approximation, which can be used to scale falsification. Have you thought about it?
Sorry, can you repeat the question? Can you repeat?
If you consider similar ideas for under-approximation, so this can be used to make falsification faster. So have you considered that? Have you thought about it? So in your talk, you're using over-approximations to make the verification faster, and the other direction would be to use under-approximation to find counterexamples faster. So if you thought about this.
I think that it also helps to find the counterexample faster, because the verification, the NP completeness, the performance is better. The performance of the verification tool is better because we actually generate a smaller network.
Right, but you don't know if that counterexample is a real counterexample, right? So the question was really if you use this thing directly to do the under-approximation to directly find real counterexamples, basically. If you thought about
this is what the indicator-guided abstraction method was aimed to generate, but we don't use it because the first method, the abstraction saturation method, was better according to our experiments.
Okay. Okay, then 2 questions then from Theodora. So thank you for the talk. And there are 2 questions. So what's the difference from using a triangle approximation for each ReLU with possible refinements using mixed integer programming and your technique? That's one question.
Sorry, I don't hear. I didn't hear.
So she asks, what's the difference between using the triangle approximation for ReLUs with possible refinements using mixed integer programming and your technique?
I don't know about the triangle. So Guy, maybe you can answer if you are here.
I guess I have to unmute.
Sorry, I don't know about the triangle approximation, so I cannot answer.
Okay. All right. Well, the next question is if your technique could be used for compressing or explaining network predictions.
Okay, so we start to think about that, but currently our approximation cannot be used as a compression tool. It can, but the accuracy of the compressed model is really changed because our outputs are much bigger.
Okay, then one last question is, if do the experiments take into account the time needed to compute the over approximation before checking the property? Nice talk.
So I don't sure about that. Okay, so in the current version, yes, we take all the time, also of the generating of the over approximation itself. But this is not so. It's relatively negligible because
Okay.
the pre-processing and all of that is short in time.
Okay.
Time. And one point, I understand the first question only now, so I can say that we encode for cases of multiple outputs, we actually generate the property. We encode the property of conjunction. If we have some property with conjunction or disjunctions, we can encode this property by using the last layer. We add the last hidden layer, and then we apply all the process as the original process.
Okay, great, thanks. So let's go to the next talk. So the next is the speaker is Hong Dong Tran from Vanderbilt University, and he will present a generalization of the star set approach for the verification of convolutional neural networks.
Hello everyone, my name is Tran from Vanderbilt University. So today I'm going to talk about verification of deep convolutional neural networks using the concept called image star. So the main motivation of our research is that well-trained and accurate convolutional neural networks are vulnerable to adversarial attack, where slightly changing the input can lead to a huge change in the output result. So this behavior is very dangerous when we want to apply convolutional neural networks in safety critical applications like autonomous driving cars. Therefore, it is very important to have methods that can formally verify the robustness of convolutional neural networks under adversarial attack. So this slide shows the general idea of our approach for verifications of neural networks. Suppose we have a neural network F, and then we have the input set I. So we want to compute the output set Fi that contain all possible outputs corresponding to the input set I. And then we have a property P, which is the predicate of the output space of the network. And then the verification problem is that we're going to check whether the output set Fi intersect with the property P or not. So if intersect with the property P, we say the property P is satisfied, otherwise unsatisfied. So to do reachability analysis specifically for convolutional neural networks, we propose a new concept called image star, which is an extension of the star set that is used in hybrid community to do reachability analysis for linear system. So an image star is a tuple that contains a center image, a basic images, and a set of predicate variables. And to bound the set, we have the constraint on the predicate variables. So any image in an image star is a linear combination of the center image and the basic images. And to bound the set, we have a constraint on the predicate variables. So we can see that an image star represents a set of infinite number of multi-general images. So using image star, we can do reachability analysis for different layers of a convolutional neural network. I'm going to show you how to use image star to do reachability analysis for convolutional layer, average pooling, mass pooling, fully connected, batch normalization, and ReLU layers. So these layers are the most popular layers used in convolutional neural network. On the right-hand side, we have an example of convolution operations. And I'm going to show you that for this type of linear operations, we can use image star to do reachability analysis very efficiently. So now I'm going to show you how to do reachability analysis for convolutional layers using image star approach. So suppose we have a convolutional layer, and then we have an image star input set theta, and then we want to compute the output set of the layers. So the output set of the layers, theta prime, is another image star, in which the new center C prime and the basic image Vj prime can be efficiently constructed by applying the convolution operations on the center and the basic images of the input set theta. And in this reachability analysis, the predicate of the output set theta prime and the input set theta are the same. Because the average pooling also another linear operations, so the reachability analysis for an average pooling layers is very similar to the reachability of a convolutional layers. So I'm gonna skip this in this talk. So similar to the convolutional layers, the output set of fully connected layers can be constructed very quickly. Basically, the center and the basic images of the output sets are the alpha mappings of the center and basic vectors of the input set. And in this case, we also have the predicate of the output set and the predicate of the input set are the same. So like a fully connected layers, the output set of a batch normalization layers is also an alpha mapping of the image star input set. And the center and the basic images of the output set can be computed very quickly by just scaling the center and the basic images of the input set. So now I'm going to show you how to compute the output set of a mass pooling layers exactly and approximately. So the idea of a mass pooling operations is that if we have a single input image, we need to find all mass points of all local regions of the input image to construct the output image. So now we have the input is an image star, which is a set. So we also need to find all mass point candidates for all local regions of the input set to construct the output set. And in this example, we have an image star with 4 local regions, 1, 2, 3, and 4. So the question here is that what are mass points of these regions? And the challenge here is depending on the value of the predicate variables, each local regions might have more than one mass point candidate. So in this example, one can see that for the local regions 2, 3, and 4, there's only one single mass point candidate for these regions. However, for the first local regions, we have 2 mass point candidates depending on the constraint on the predicate variables alpha. So after finding all mass point candidates of all local regions, we can combine them to construct the exact output set of a mask pooling layers. So in this case, because the first local regions have two mask point candidates, so the output set of the image star is going to be two image stars. The first image star is the combinations of the first mask point candidate with other mask point in other regions, while the second one is the combination of the second mask point candidate with other mask points in other regions. And you can see that from a single image star, it's going to be split up to two new image stars. And if other local regions also have more than one mask point candidate, the number of image stars is going to grow exponentially. So to overcome the explosion in the number of image stars in the exact reachability, we propose an over-approximation method to over-approximate the exact reachable set of the layers. So the idea is that if the local regions have more than one mask point candidates, we're going to introduce a new predicate variables. Here is beta. So this predicate variable is going to represent the mask point candidates of the local regions. And to be the mask point, this new predicate variable need to be larger than all mask point candidates in the local regions. And it also need to be bounded by the largest upper bound of all mask point candidates in the local regions. And then we're going to combine this new predicate variable with other mask point candidates in other regions to construct a single over-approximate reachable set for the layer. So now I'm going to show you how to compute the reachable set of a ReLU layers exactly and approximately. So the exact reachable set of a ReLU layer can be computed by performing a sequence of step ReLU operations. So a step ReLU operations compute the output set as a specific neuron or pixel in an image star. So let's consider how a step ReLU operations work on the first pixel of this 2x2 image star. So at this pixel, we have the value of this pixel is -1 plus alpha. And now, if alpha is larger than 1, then when we apply the ReLU's activation function on this pixel, we're going to have the output is the same as the input. However, when alpha is smaller than 1, then the output of this pixel is set to be 0. So we can see that in the exact reachability of a ReLU layers, after one step ReLU operations, one single image star can split into two new image stars. So in the worst case, the number of image stars in the reachable sets grows exponentially. So to prevent the explosions in the number of image stars in the exact reachability, we propose an over-approximations method to construct a single over-approximations of the exact reachable set of ReLU layers. So the idea here is that we replace the step ReLU operations by an over-approximate step ReLU operations. And this over-approximate step ReLU operations gonna over-approximate the exact reachable set as specific neuron by a triangle. And in comparisons with other methods like sonotop or the recent new polytope abstract domain methods, we can see that our over-approximation rule is less conservative than the sonotop and the new abstract domain methods. So I have briefly described how the image star approach works on different layers in convolutional neural networks. So for implementations, we implement the image star approach in the tools called NNV, a neural networks verification tools for deep neural networks and learning-enabled cyber-physical system. So for evaluations, we evaluate the image star approach in comparisons with the sonotop and the new polyhedron abstract domain methods from ETX series on a set of convolutional neural networks trained on the MNIST dataset and the VGG's network. So on the verifications of MNIST network, we consider the robustness of the networks under the darkening attacks on 100 images. So the idea of a darkening attack is that if you have a pixel xi that have the values larger than a threshold d, then it's going to be darkened into the new values xi prime in the range between 0 and delta time xi. So these pictures show you the ranges of 10 elbows of the small MNIST network using different approaches for a specific value of d and delta. So from these figures, you can see that the zero-top methods can give you a very conservative ranges. And the polytop approach gives much better ranges than the zoom-top. And the image star methods give you a tightest ranges in comparisons with these other methods. So this table shows you the comparisons between the image star methods and the deep learning methods on the medium MNIST networks. So from this table, you can see that the image star approach proves much more cases than the polytop approach, especially for the case that delta is large, which gives you a larger input set, and d is small, which gives you more number of pixels per attack. And from this table, we can also see that the image star is faster than deep police in the verifications of the medium network. So this is the comparisons between two approaches on the large MNIST convolutional neural network. From this table, we can see that the image star is much faster than polytop approach in the verifications of the large network. And the polytop approach runs into memory issues in some cases. So this table is the comparisons between the image star approach and the polytop approach on the verifications of VGG networks under the different adversarial attacks. So on the left-hand side of the tables, we have else is the percentage of the attack we apply on an image, and delta is the size of the input set around the attack. And from this table, we can see that when the input set is small, then the polytop and image star approach give very similar performance in both conservativeness as well as the verification time. This table shows you the comparisons between the exact and the approximate analysis on VGG networks on a single image. So from the table, you can see that the approximate analysis is faster than the exact ones. However, the approximate analysis might return unknown results in some cases because its reachable set is an over-approximate reachable set and conservatives. So there are some cases that they cannot verify the network is robust or unrobust. These figures show an interesting cases where a bell pepper is misclassified as a strawberry under adversarial attack. So using exact analysis, we can prove that the network's VGG19 is not robust in this case, and we can generate the adversarial image or counterexample image. However, using the approximate analysis, we cannot prove that the network is not robust because of its conservativeness. So in practice, it is very important to know what kind of convolutional neural networks that are verification friendly. So to know that, we need to know what kind of layers that dominates the total reachability analysis time. So this figure shows you the reachability time of different layers in VGG19. And you can see from this figure that the mask pooling and gradules dominates the total reachability time. So in practice, if you train a convolutional neural networks and you neglect the mask pooling and minimize the number of values in the networks, then you can have a good network and verifications friendly networks at the same time. In conclusions, we have proposed the image star approach for the verifications of convolutional neural network, and our approach is less conservative than the zonotop and the polytop approaches, and we have shown that the reachability for mask pooling and value layers is time-consuming. So for future works, we're going to improve the scalability of the image star approach, as well as working on verifications of semantic segmentation network and recurrent neural network. So thank you very much for your attention, and I'm ready for any questions.
Okay, thanks for the talk. Tran, can you turn on your camera and mic? So we have two questions. So the first one is from Yuhao Zhang. I hope I don't butcher your name. Thanks for the nice talk. It's surprising to see that image stars is better than deep poly, both in precision and speed. Can you elaborate more on why image stars is faster than deep poly?
So thank you for the questions. So we, to be able to plot the ranges of all the methods, we implement the deep poly methods in NNV. And we know that in NNV we use MATLAB, so the runtime should be like slower than the original implementations of deep poly. So that's the first effect. The second one is that we represent the over approximations like the triangle proposed by deep poly by also a star set or image star. We can do it. And then what we see in the experiments is that when we have a larger delta, then the deep poly tends to be more conservative and when it's more conservative, it introduce more predicate variables, and then it's gonna give you more time to do to solve LB problem when you try to construct the reachable set. So I think that's the two main reasons that why the image star approach is faster than deep poly in medium and large network. So I think the main reasons might be the implementations, not because yeah, I think the maybe when we compare directly with Iran in implementing Python, I think maybe Iran's gonna have a better verification time. Yeah, but to be fair comparison, we need to implement the methods in both, like in the same platform. Thank you.
Okay, thanks. So we should wrap up, but there are just two questions. Maybe we can answer quickly. So from Theodora Baluta, she says, thanks for the talk. And she asks in slides 20 and 21, if she remembers correctly, what are the D and I think L or I parameters in the tables?
So D is the threshold that's if the value of a pixel in the image larger than that threshold, you're gonna attack it, like darken that pixel. And delta is how large of the darkening, like you can darken the pixel to the value between 0 and delta times xi, something like that. So that's the two parameters for darkening attack.
Okay, and then the second question is for VGG. The verified perturbation sizes were rather small, 10 to the power of -7 from her understanding. Is that correct? And why is that the case?
Sorry, can you?
She's wondering if the verified perturbations that you used for VGG were rather small, and if that's really the case, and why is that? Why
so that's a very interesting questions. So basically, when we do verifications for very deep network, we realize one fact that a very deep network is very sensitive to a very small noise, right? Even for like very small, you cannot see the noise, the attack, then the attack still affect the verification result. So that means That means in our paper we focus on like the attack that you cannot see, but it's still relevant. It's still very important, and you can increase the number of delta. However, when you increase the number of the inputs, the range of the input set, then you're gonna cause many explosion in the exact analysis, right? The number of images are gonna explode very quickly. So in the worst case, grow exponentially. So you're gonna see there may be some memory problem or like computation time increase a lot when you increase the input set. So I believe that in the future, comparisons, the conservative need of different approaches is very important, because when you increase the input set, then you can see that the performance of different methods clearly. So some methods can be very fast, like Iran or deep zonal or deep poly. However, when you increase the input set, then they become very conservative, and the result, they cannot verify the robustness of the network. So yeah, thank you.
Okay, thanks. All right, let's move on to the next talk. So the next speaker is Dong Xu from the University of Virginia, and he will present a framework for generating benchmarks for neural network verifiers.
Hi, I'm Dong Xu. I'm very honored to have this chance to present our work, Systematic Generation of Diverse Benchmarks for DNA verification. This work is done by my colleague David Shriver, our advisors Matthew Dwyer, and Sebastian Album, and me. For starters, I would like to share the agenda of this presentation to give some hints of what's coming up. Firstly, I would like to state the problem we're trying to solve by asking two questions. Why do we need benchmarks in the verification community? And also, what makes a good benchmark? Then, I will discuss how good benchmarks can be built. Afterward, I will talk about our approach and its instantiation, GDVB. Lastly, I will share some results and use cases of a preliminary study and some interesting findings. The first question we're interested in answering is, why do we need benchmarks? Despite the emphasis of verification is the development of theoretical and algorithmic techniques, the community has learned a lot that empirical study is also a crucial part of advancing the field. It helps researchers to understand how different algorithms and implementations compare. Benchmarks have also been used in a wide areas of verification community since at least 1994, such as SMT, SAT, serum proving, model checking, software verification, and so on. Many of these benchmarks are used in verification competitions. According to 6 years of SMT-Comp, a certain software presents a key idea that improves the performance in a particular division, and this idea is implemented by most softwares in the following SMT-Comp editions. This tells us that good benchmarks can help identify the superiority of certain algorithms that further lead to steady improvements of tools' performance in the field. From studying the existing benchmarks in the verification community, we found two main objectives that they aim for, which are assessment of state-of-the-art and comparison of alternative approaches. For the past 3 years, it has emerged more than 20 DNA verification algorithms that do analysis insights from search, optimization to reachability. When we are all excited about the fast development of the field, the problem comes. How do they compare? The fact of missing such benchmarks in the DNA verification field has led researchers to choose a limited set of test cases that others have used, or that their tools can be demonstrated on. Different verifiers are also evaluated on quite different DNA architectures on different tasks. For example, Relublex and Marabou used the ACAST artifact, whereas Iran and Urify used MNIST. We found it very difficult to cross-compare different DNA verification algorithms without a good benchmark. Similar to the benefits of benchmarks in other fields, good DNA verification benchmarks can differentiate various algorithms, analyze how they perform on state-of-the-art neural networks, and also help to advance DNA verification research. By understanding the advantages and drawbacks of various DNA verification algorithms, researchers can adopt key ideas to invent new methods. Thus, we believe having high-quality DNA verification benchmarks is a place to start. By studying the benchmarks in the verification field, we extracted 3 key requirements that makes good benchmarks. They are diversity, representativeness, and evolvability. Diversity asks for variance in the structure and difficulty of the benchmark problems. For example, the theorem proving benchmark stated that the benchmark should contain problems varying in difficulty. Representativeness means the problems should reveal real-world use case. For example, also in the theorem proving benchmark, they asked that the benchmark should span a diversity of subject matters. And evolvability requires an easy solution to evolve the benchmark to keep the problems up to date. For example, the set competitions require competitors to bring your own problem to form the benchmark every year. Equivalently, we think diversity, representativeness, and evolvability are also key elements of successful benchmarks in the DNA verification field. Now we have understood the requirements of high-quality DNA verification benchmarks. I will then discuss the approaches that we took to tackle them. Firstly, we want to understand what makes diversity in DNA verification. To answer this question, we performed a study of how existing verifiers vary when some aspects of the verification problem change. We measured verification tools' performance in terms of verification time and accuracy. As a result, we identified 9 such factors that affected some verifiers in various settings. For example, by varying the number of neurons in the neural network where other aspects are fixed, we can see that verification time increases with the number of neurons. Also, by varying the input domain size of the neural network where other aspects are fixed, we can see that verification accuracy can decrease with increasing input domain size. Again, the intention of the factor study is to find characteristics of verification problems to challenge verification tools at most. We found an incomplete set of 9 factors as a start point, in which 8 of them can be easily controlled. A level for a factor simply means its choices of values. For example, for the input dimension factor, one possible 5-level setting is to have quintile with respect to the original input dimension. And for constraints, it defines the restrictions of the level choices among different factors. For example, the number of fully connected layers and convolutional layers cannot be 0 at the same time, as it will result in an empty network. Now I will talk about how good DNA verification benchmarks can be built. We took a generative approach that synthesizes benchmarks from a seed verification problem. This guarantees that the outcome benchmark will meet all 3 requirements. When using parameterization with seed problems from different problem domains, will ensure diversity and representativeness of the benchmark. The covering array technique will further enhance diversity. When using parameterization with different seed problems and customized factor levels, will also improve evolvability. We define the DNA verification benchmark to be a set of verification problems where each instance is a pair of network and property. For example, a property can ask whether the neural network produces outputs that are constantly greater than 0. We then realized our ideas into a tool called GDVB, Generator of Diverse DNA Verification Benchmark. It consists of 3 main modules. The first module is a covering array generator. It takes a factor-level combinations, constraints, as well as strengths, and generates a covering array. A covering array is an n by k array that each row is a configuration of the factors. in which all choices of factors are covered at t ways with the satisfaction of the constraints. For example, we have three factors: number of fully connected layers, number of convolutional layers, and number of neurons. Each of them has two choices. Based on the constraints we mentioned earlier, a pairwise covering array will cover all pairs of choices for these three factors within 5 configurations. The intention of covering array is to reduce the test swing size while maintaining the interesting behaviors of problems where combinations of factors are considered. The second module then uses the seed verification problem and converts a covering array into a set of verification problem transformations, such as drop layer number 3, scale property size to 75% of the seed problem, and so on. Lastly, we use these transformations and refactor the neural network and property into a set of instances in the benchmark. We then evaluated our approach on the Div2 network. It has 5 convolutional layers, 4 fully connected layers, with more than 82,000 neurons and more than 2 million parameters. We configured 6 factors into 5 levels and 1 into 6 levels. The total exhaustive factor combinations will be more than 93,000. Thanks to covering array, GDVB only produced 44 verification problems at pairwise strengths. We use GDVB to generate benchmark, and to show its use case, we ran 5 verification tools on it. Here is a plot that showcases the diversity of our benchmark for the Div2 network. The x-axis represents 5 factors: number of neurons, number of fully connected layers, and number of convolutional layers, input domain size, and input dimensions. The y-axis shows the levels normalized to the range between 0 and 1. For example, for the number of fully connected layer factor, the 5 levels are the number of fully connected layers ranging from 0 to 4. The purple dotted lines shows the combinations of factor levels of the problem instance in the benchmarks generated by GDVB. For example, the green line shows a benchmark problem with 20% neurons, 3 fully connected layers, no convolutional layers, 60% input domain size, and the same input dimensions to the seed network. The red dotted line is a test case used in the Neurify paper. You can see that our approach can generate much more systematic and diverse benchmarks. We then plotted the number of accurate properties for each verifier over the above benchmark. We can see that technologies advanced so quickly in this area. For Planet and Reluplex being the leaders of the field, were overtaken by NeuronDP and Neurify just within 2 years. Also, we found that BAB and BABSB being the improved versions of Planet, but didn't perform quite as imagined. We also plotted a radar graph that showcases how each verifier reacts when the levels of factors vary. In each subplot, the hexagons with solid lines are the maximum levels the verifier achieved over 44 test cases, and the dotted lines are the median values. Recall that NeuronDP and Neurify performed similarly in the box plot. In fact, they reflected differently in terms of factors. By looking at the median value, we can see that NeuronDP can handle neural networks with more convolutional layers than Neurify, but fewer input dimensions. To conclude, in this talk, I covered the importance of having good benchmarks in the verification community and lack of such in the DNA verification field, shared our approaches of generating such high-quality benchmarks, and pointed its use case and some interesting findings. In the future, we plan to identify new factors that affect verification tools' performance and cover a broader range of verification tools to do a more thorough study. Here is a link to our GDVB tool. You're welcome to read more details in our paper and try our tool. We are open to any questions and suggestions you might have, and encourage researchers to contribute as well. Thank you so much for listening.
Hello, everyone.
Okay, thank you. So Dong, are you here? Can you? Okay, hi.
Yes, hi.
So thanks a lot for the talk. So okay, there is a question from Stanley Back on the Slack channel, and so he asks, are there plans to generate benchmarks in the VNN lib format for use in future verification competitions?
Yes, we have actually been contacted by the host of the VN competition, and I think we are excited to be participated in generating competition benchmarks, yeah, for the future.
Okay.
Currently, we use the Onyx format as a model. So I think they are also using this format, which is a good sign.
Okay. The next question, so we're running a bit behind. So the next question is from Teodora Baluta, and she says, great initiative. Thank you for the talk. Do you take into account the accuracy of the generated neural networks?
Yes, we tend to distill networks that has as high accuracy as possible. But for now, we don't consider accuracy as a factor, but it could be included in the future.
Okay, excellent. So there are two more questions on the Slack channel, but since we are a bit behind, I'll just move on, and I invite you to go on the Slack channel to reply directly. There are just two more questions. Thanks.
Sure. Thank you.
Okay, so the next talk is again by Hongdun Tran, and he will present the NNV tool for the verification of neural networks.
Hello, everyone. My name is Trent from Vanderbilt University. So I'm going to present NNV, a verification tools for deep neural networks and learning-enabled cyber-physical system. So NNV is available online at a very vital GitHub account, and it is implemented in MATLAB. However, a user can run NNV without MATLAB installation through CodeOcean. So the center of NNV is reachability solvers that can be used to compute the reachable set of a feedforward neural network or a neural network control system or convolutional neural network. And these reachable sets can be used to verify a safety property or robustness property of a network or a safety property of a neural network control system. And the reachable sets can also be used to visualize the behavior of a network or a neural network control system. So this table shows the main features of NNV. So in NNV, we support exact analysis and over-approximate analysis using different types of set representations, including star set, polyhedron, image star, Zolotope, or the new polytope abstract domain methods from ETH Zurich. And currently, NNV supports most of popular layers used in convolutional neural networks, including mask pooling, convolution, batch normalization, average pooling, and fully connected. So in NNV, we support parallel computing, so users can speed up verification by increasing the number of cores used in verification. And NNV also supports the falsification and counterexample generations. In this video, I'm going to show you how to use NNV to verify the robustness of a convolutional neural networks under adversarial attack. So there are three steps for doing that. First, we need to pass the networks already trained into NNV and construct an NNV network. So here, I suppose we have a Keras model, trained in Keras, and then we use import Keras network function in MATLAB to pass the Keras model into MATLAB and construct the net object in MATLAB. And then we're going to use the class methods in CNN class in NNV to construct the NNV object. So that's how we construct the NNV network object. Now, the second step is that we need to construct the input set corresponding to the attack. Here, we consider the L infinity norm attack. So you need to load the image, and then we apply the attack in the image and on the image. And the epsilon values here is equal to 0.002. And then we're going to construct the lower bound and upper bound of the image under the attack. And then we construct the image star input set using the image star class. And now we're going to verify the robustness of the network under the L infinity norm attack. And then we're going to verify the robustness of the networks using the verify RBN, the methods. That means robustness methods, verify robustness methods. So the inputs to these methods gonna be the input set, the correct ID, the reachability methods. I choose the approximate star, and then the number of calls we want to use for verification. So now I'm gonna run the code. You can see that it's gonna compute the reachable set of the networks corresponding to the input image star, and then it's gonna use the output set of the network to reason about the robustness of the network. So that's how it works. You can also plot the reachable set or the ranges of all outputs of the networks by just get the output set and then estimate the range and then plot the range as you want. And you can see that from the range visualization, you can see that the output corresponding to the digit 7 always larger, always the maximum one. So that means the network correctly classify the image as the digit 7. Now I'm going to show you how to use NNV to verify a safety property of a neural network-based adaptive cruise control system. So in this system, we have two cars, and the goal is we control the able car to keep a safe distance with the lead car. And the safety requirement here is that the actual distance between two cars is always larger than a safe distance. And depending on the initial condition of the lead car, then the system might be safe or might be not. So for the first case, when the lead car is moved a little bit slow, then there's the case that the actual distance is smaller than the safe distance. And so in this case, the network is unsafe. However, when the lead cars move a little bit faster at the beginning, then the system is safe. So in summary, we have introduced NNV, verification tools for deep neural networks, and a learning-enabled cyber-physical system. So the core of NNVs are the reachability schemes working on different setup representations. For example, polytron star, image star, zoom and news polytron abstract domain methods. For future rules, we're going to improve the scalability of NNV. We're also working on semantic segmentation network verification, recurrent neural network verifications, and direct acyclic graph network verification. So NNV research is funded from NSF, DARPA Azure Autonomy, and the Air Force Office of Scientific Research. Thank you very much, and I'm ready for any questions.
Okay, thanks. Let me see this. So on the Slack channel, there are no questions for now, but maybe since you said you didn't have time to talk about it, maybe you can do that in this couple of minutes that we have. So how does NNV compare to the other approaches? Like, yeah.
Yeah,
maybe a
so I
few words
didn't
about that.
present. Yeah, I didn't
Yeah.
present in the talk. Yeah, but you can find the paper. So
Mhm.
generally, NNV is faster than Marble and Riddle-Blast from Stanford when we run on multi-core machines. And NNV also less conservative than deep poly and deep zonal methods. It's lower, but it's less conservative. We can prove more properties than deep poly and deep Z. Yes, so I think Stanley Bot already presented at the beginning how to improve the store set methods to make it like 10 times or 100 times faster than the current NNV implementation. Yeah, thank you.
Okay, so the implementation is in MATLAB, right? You said?
Yes, yes.
So why that choice?
So yeah, so at the beginning I want to choose like Python. I prefer Python. However, when I want to visualize the reachable set, so there are the tools called MPT Toolbox from ETH Zurich. So they support the visualization of polytope. So so I use it. So I implement everything in MATLAB. But I think in the future I gonna view another tools using Python because the timing performance is much better in Python.
Yeah.
And in Python, they are also very easy for like explore parallel computing. So so in Stan talk, he talked about the deep first shot, right? So in MATLAB, it's very hard for you to handle multi cores when you implement the deep first shot methods for star set. You need to handle multi-cores at the same time, and then how to stop one core when the other core have the result. So in the future, I think we're gonna move NNV to Pythons. Yeah, and we can support mostly everything's trained with PyTorch or Keras. So right now, NNV work well for deep learning toolbox. So when you train a network on deep learning toolbox, then you can use NNV to automatically construct the object and then do verifications. So very, very efficiently. Yeah.
Okay, thanks.
Thank you.
Okay, so I think this concludes the session. Thanks a lot to the speakers for the talks and to the attendees for the questions. So now I invite everybody to join the breakout session. So the links are on the online program on the CAV website. And yeah, I'll see you there then. Thanks.